We continue on this lecture for chapter 9. This is part 3. And for this part, we will look at the last remaining items from 6 to 9. That is, first we'll look at up-down synchronous counters, which are found in section 9-4 of the book. We'll then move on to cascade counters, which is 9-6, and then move on to counter decoding 9-7, as well as finally conclude with 9-8, which is counter applications. So on the matter of up-down counters, so up-down counters are counters which can progress in any direction. That is, they can count either up or count down. So they are bidirectional in that sense. So the specific count sequence, for instance, if it's counting up U for up, it will count from 0, 1, 2, 3, 4, and so on and so forth. And then when it reaches the terminal count, say 7, it goes back to 0. That would be an up count sequence. A down count sequence D would be from 7, 6, 5, 4, 3, 2, 1, and then it goes back to 0, and it repeats. So for this section, we'll look at two types of the 3-bit counters. We'll just look at an example of a binary up counter, how we can design that, and then we'll also look at designing a Cray code up-down counter. So in actual fact, the counter will effectively look like this at the highest level. There will be 3 bits, the 3-bit output which will give you a count, and then there's an input Y, which will signify when Y it's held low, it will do a down count. That is, it will do 7, 6, 5, 4, 3, 2, 1, 0, 7, 6, 5, 4, 3, 2, 1. Whereas when Y is high, it will count upwards, like the normal counter does. And then the counter should also have a clock input. So the design exercise basically is to determine what should go inside, what type of circuitry should be inside the counter itself. So first, let's consider the binary counter. So the binary counter, as we have illustrated, if the signal is held high or there is an up signal, the counter will move from 0 to 1, from 1 to 2, from 2 to 3, and so on and so forth, if we look at the state diagram. But whenever the signal changes to down, then the counter will start counting downwards. From 4 to go to 3, 2, 1, 0, 7, 6, and so on and so forth. If the signal is down, if the signal is up, it will go the other way around. So you can see here, in fact, that because we want to design a 3-bit counter, we are going to be using 3 bits, and so we need 3 flip-flops, each representing each bit of the counter. Now, so if we look at the design process here, we'll just try and do an ad hoc design whereby we look at the way the bits of the counter change the output. So we'll not go through the exercise of designing it in the form of a final state machine. But when we are considering the create bit counter, we'll just go back and see how we can apply that procedure of designing a final state machine to design this up-down counter. So for now, we'll just make observations and use those observations to design. So first of all, the table here, 9-6, gives you the counting sequence. So the counter will begin from 0, 1, 2, 3 in this direction. If it's an up count, it's counting upwards. So if it's a downward count, it will go in the opposite direction. 7, 6, 5, 4, and so on and so forth. So this will be a down count. And here we can see that this up count maps this sequence, and then the down count maps that sequence. Now, if we are going to use JK flip-flops, in this case, this is the transition table for the JK flip-flops. This is the transition table for the JK flip-flops. We see the different transitions here. This is in transition to remain in 0. This is a toggle transmission when it moves from 0 to 1. This is another toggle transmission where it moves from 1 to 0. And then this transition remains at 1. And these are the input of the JK flip-flops that must be held so that the transitions are executed. So let's look first at what happens to the 0th bit of the JK flip-flops, Q0. So on the listening bit of that counter, we see that in fact when the counter goes up, so in the up count direction, this is the up count direction, we see that in fact what happens is that the counter moves from 0 to 1, from 0 to 1, from 1 to 0, 0 to 1, 1 to 0, and so on and so forth. So it changes 0 to 1, 1 to 0, and so on and so forth. If we look at the down count, on the other hand, we start here and look at the down count going up. It counts from at 7, Q0 is 1, at 6, Q0 is 0, at 5, Q0 is 1. So it changes, it keeps on changing 0, 1, 0, 1, 0, 1. So in fact, it looks like it doesn't matter. The direction of the count doesn't matter. So whether it's counting up or down, it doesn't matter. What matters is that the counter itself will always be changing from 0 to 1, 1 to 0, in spite of the direction of the count. So we see in this case then we can observe that what seems to be happening is, in order for us to achieve the 0 to 1 transition, in order for us to achieve this transition, what needs to happen is that the input of the JK flip-flop is that the J has to be 1 and the K doesn't really matter. In order for us to achieve the second transition, which is 1 to 0, what needs to happen is that the K needs to be 1 and the J doesn't matter. So if you combine these two, you will realize that in fact to maintain both of these transitions, we have to have a J which is 1 and then a K which is also 1. If you combine these two. So in this case then we observe that J0, which is the input of the JK flip-flop, number 0 has to be 1. K0 also has to be 1 in order for JK flip-flop 0 to always be changing or toggling. We're moving on then to JK flip-flop number 2, the second one, which is Q1, and try and establish what the inputs need to be. So for JK flip-flop number 2, these are the observations that we'll make. We observe that when we are in the direction of an up count, this is the direction of an up count, Q1 changes only when Q0 is 1. So let's look at Q1 in this direction. So we see that Q1 here remains from here to here, it remains at 0. But the moment that Q0 was 1, Q1 also changes to 1 in the next transition. Here it's 1. Here it will remain at 1 because the Q0 was 0. But the moment Q0, the previous Q0 becomes 1, Q1 will change to 0. So every time Q1 is 1, there is a change. There is a transition from 0 to 1, or 1 to 0, or 0 to 1. So here there is a transition from 0 to 1. Here there is a transition from 1 to 0. This is a transition from 0 to 1. So every time you have, in the case of an up count, whenever Q 0 is equal to 1, the Q1 will change. Q1 will change. This means, therefore, we can say that J1, because J1 here, for this transition to happen, J1, for the transition of 0 to 1 to happen, J1 has to be 1. So we can say J1 has an element of U times Q0. For the transition of 1 to 0 to happen, K1 must also be 1. So we know that then it means there's a part of, at least in that direction, U times Q must, the logic input for J1 must be so that it maintains a toggling transition, that is, it maintains a 1 when U is high and Q0 is high. Now let us look at also the downward transition. So the downward transition is when you move this way. So that is the downward transition. Let me grab that off. So we look at the downward transition or the downward count when the counting goes in this direction, as this signifies. So when the counting goes in that direction, we see that whenever there is a 0, you see here, the 1, when the count goes down, here the 1 remains, it's a 1. In the next number, it remains a 1. But here there's a transition. And this transition happens because Q0 here was 0. In this case, there's a 0 here. Here the 0 remains. But this one, there's a transition here. There's also a transition here. So this transition happens because the Q0 was initially 0. And here we also see a transition of Q1. And when we look at the previous Q0, we see that it was a 0. So we see that whenever there was in the downward direction of the count, that is this direction, we see that the output of Q1 changes only when there was a downward signal and Q0 was low, basically. So we see that it changes when Q0 was low. So in fact, J1 and K1 have to be then the input equation of K1 and J1 have to be the values U times U and Q0, or D and Q0 bar. If U is taken to be the upward signal and D is taken to be the downward signal. Using the same observation, we can see that on the upward count, Q2, now focusing on Q2 changes only when Q0 and Q1 are 1 on the upward count. So it changes only when both Q0 and Q1 were up in the upward direction. This is going to change. This is going to cause a transition. Otherwise, nothing will happen. You see here as well here. This will cause a transition because now the next group here, the next bit here is going to be this 0. So in the same light, we can see that when we are in the downward direction, we see that whenever, so the downward direction, that's when you have this counting from here to there. We see that whenever both Q0 and Q1 are low, there is a transition. Whenever both of them are low, then there should be a transition here. Because this transition, it means the next bit is going to be this one. So we can write then the equation that up times Q0 times Q1 or down times Q0 bar Q0 Q1 bar. And the same goes on for the K. So the J is equal to the K. So because of that, we can now design, given these input equations, we can now design the up-down binary counter, where this is our input Y for up, where Y is kept high for up and down for low for down. Yeah. So because of that, we can see that J0 K0 is equal to 1, which is that, and then J1 K1 is equal to this OR gate, which is that, combining D, the up, combining D and Q0 bar, combining the D, which is the knot of Y here, with Q0 bar, and then all of this goes into that, and then also combining U and Q0 bar, so the up count is combined with Q0, and so this gives you that flip-flop. So in a similar manner, you are able to determine J2 and K2. So go over this logic as you read in your book. This is an example that's also given in the book, and see how easy then it can be to design this up-down counter. However, you will see this analysis is not as intuitive as using the previous steps that we have learned on designing the final state machine. So let's test then that five-step design procedure for designing an up-down counter. This time around, let's look at the 3-bit up-down counter that counts in the Cray sequence. So remember the Cray sequence. The Cray sequence doesn't use the ordinary binary. We said from digits 1, you'll remember that Cray sequence is the sequence whereby the difference between the two adjacent numbers is just 1 bit. So starting from 00, we will move to 001. We will then move to 011. So there's a single bit change in each one of those. So in this case, we imagine that we have an input Y. When Y is high, this is up. When Y is low, this is down. And because this is a 3-bit counter, we will realize that we need 3 flip-flops to implement it. So this is the state diagram for this binary 3-bit binary counter. So after drawing the state diagram, the next step is to establish the next state table. And the way the next state table is being done in this instance is that we separate the next state into 2 different next states for when it's counting downwards and for when it's counting upwards. So we can see that if it's counting, if the present state is 000 for that Cray code counter, then when the count is downwards, then it will go to the last final count, which is 100. Otherwise, if the up count is high, that is the Y input is high, it will go to 001. So it's just a bit unconventional there, but the process is the same. So when we go to the flip-flop transition table, now what we will be looking at is to consider how then the inputs, in this case the inputs, the present state and the input. So at the inputs, we are going to be looking at the present state as well as the Y input. How this present state and the Y input have to be set so that they can determine this next state, either this one or that one. So we know in this case, in the first instance, if the Y input is 0, then this corresponds to that bit. If the Y input is 1, the green bit, then it will correspond to this transition. And so we are also mindful of the fact that the way the flip-flop works is, if we want to quickly do a summary, we see that the input K here is important when the present state is 1. And the input J is important when the present state is 0. So we can tend to ignore, for the input J, we can ignore this other part. Here we can only consider for the input K. So let's see how we can use that. So in this instance, let's say we wanted to create the map for K2. We wanted to create a map for K2. So what we will look at now, we're saying if we are going to look at K2, it means we focus for when the input is 1, when the present state is 1. And because it's K2, we'll just look at this particular Q2, what Q2 should be. And in this case, remember, the way the inputs are, it's going to be Q2, Q1, Q0, as well as the input Y. And so we can draw, because now it looks like we have a K map of 4 variables, Q2, Q1, Q0, and Y. We can draw a 2x2 K map with 16 squares. So we then zoom into the instances where the present state is 1. Let's look at those. Let's say this one, that one, that one, and that one. And let's say now we are looking at the down count when Y is equal to 0. So for when Y is equal to 0 and the next state is 1, so where do we get the transition? So if we get, let's look at where we get the transition. So if say there is a reset state here, the state changes from 1 to 0. When the state changes from 1 to 0, we know that the K input has to be 1. So let's look at that. When the state changes from 1 to 0, we see that in this instance, the state here changes from 1 to 0. And where else? Also here, we see that the state changes from 1 to 0 in the case of an up count. Remember, this portion is for the down count, this one is for the up count only. So in this instance, we can see that in fact, we have 2 cases where the transition is from 1 to 0, which means the K input corresponding to that has to be 1. So the way we can just simply summarize that is to look at these 2 instances. In the first instance here, the input would be Q2 1, the present state would be Q2, which is 1, Q1, which is 1, and then Q0, which is 0, and the Y input would be 0 because this is counting down. So this corresponds to that. So on the K map, we can plot this 1 1 0 0. On the K map, we can bring that to the K map. We can plot this 1 1 0 0 here, which means there's a 1 here. And we can look at another instance, this second instance here, where this one transitions to a 0, which means the K map has to have a 1. So in that case, we see that the present state is 1 0 0, but the Y input in this case, because it's up, it's going to be 1. So this is the entry at on the K map here. So it's 1 1 1 0 0 1 1 0 0 1. So there's a 1 here as well. So we have done with the ones, and then let's look at now the cases where we have a 1 remaining as a 1. A 1 remaining as a 1. So here we have this one remaining as a 1, another one remaining as a 1, another one remaining as a 1. So for all of these three instances here, we know that this happens because the y input is 0. So we can write up, let me just scribble here. So the present state in the first row, it's 1, 1, 1. The second one is 1, 0, 1. And then the last one here, that instance is 1, 0, 0. And the y input for all those changes is 1, 0. And we are saying all of this correspond to a k of a 0. When the transition moves from 1 and it remains as 1, the k input has to be 0. So those zeros are, so if you plot them on the k map, the first one, 11, 10, 11, 10, it's here. The second one, 10, 10, 10, 10, it's here. The third one, 10, 0, 0, 10, 0, 0, it's here. We move on to the next, we move on to the side of the up count. Let me choose a different marker. So we're saying in the case of the up count, we are still focusing on this state when this present state is, it moves from 1. In the up count, the states where the present state moves from 1 and remains 1, it's this one, that one, as well as that one. So all of this, this one, that one, that one, because we see the 1 here remains the 1 here, and then the 1 here remains the 1 here. So if we write those instances as well, the first one is 1, 1, 0. The second one is 1, 0, 1. The third one is 1, 0. Okay, the first one, oh, sorry. The first one is this one, 1, 1, 0. The second one is 111. The third one is 101. And in this case, the y input is 1 because we are talking about the up count. All of this fall under the up count. So this is 1, 1, and 1. So if we plot this on the K map, we see that we have 1101, 1101. It will have to correspond to 0 because all of these transitions is 1 changing to 1. So this will be plotted as zeros. So it's 1101, and then 1111, and then 1011. The rest therefore become don't care. Now, having that in mind, we can now formulate the groups of the K-maps. And the first group that we can make, the largest group here is that. Make that group of 2. And when we make this group of 2, we see that in this instance, as on both cases, in both cells, the Q0 remains 0, the Y0 remains 0. And then as you move up, down, up, down, up, down, Q1 remains as 1, but the Q2 falls off because it changes from 0 to 1 here. So therefore, we have, for this particular case, we have your Q1 remaining as 1, Q0 as 0, Y as 0, plus, here's another group. Another group is this. This is another group. You see? So in this group, we will see that if we move up and down from here to here, we see that Q1 remains low. Q1 remains low. Q0, it's low as well, because Q0 is low here. And Y is 1. Y is 1. So this becomes the input equation for K2. This becomes the key input equation for K2. So we can follow the same procedure and analysis to try and find the inputs for J2, to to find the inputs for K1, J1, K0, J0, and so on and so forth. And we see that, in fact, from the book, we see this then becomes the map, which we have just established in the previous slide for K2. And if you follow the same procedure, this we will find to be the map for J2. And all in all, we have J2, K2, J1, K1, J0, K0. And in this case, you can see here, in these groups here, we can verify that this group, we have QY being high, Q0 being high, and Q2 being high. But Q1, we are losing it, which is why it gives you this. And then here we can have, for the product, we have Q0 being high, Y being low, and Q2 being low. And then we have this product. So you can verify those products as well. So after this exercise, then you should be able to get all the equations for J2, K2, J1, K1, and so on and so forth. In fact, J0, K0. And using those, then you can be able to implement your counter. Now, the equations, if you write them in sum of products, this will be the equations for the J's. These then become the equations for the K's. And because here you can see that the number of there's an AND gate. There are 4 AND gates here, combining to a single big OR gate. And then you have a number of gates, and you can now reconstruct and implement your circuit here. So let's move on to cascade counters. So on the issue of cascade counters, what we say here is sometimes you can cascade, or you can link 2 counters together to achieve a high modulus of operation. So if you have a modulus 1 counter, and I say you have a modulus 2 counter and another modulus 2 counter, you can actually use the output of the previous counter as a clock signal as the input of the next stage counter. So the previous counter here, you can use this output as the clock signal of the input of the next counter, so that you can achieve a higher modulus of the counter. So cascading the counter here, you see the last stage or the output of one counter, it's driven by the output. This output is driven by the output from this one. So the clock signal only comes here. So this is a typical example, or a typical way of constructing, for instance here, the typical way of constructing the asynchronous counters. So we can use this even for synchronous counters, where we link or we cascade counters in order to have a higher values of modulus for the counters. An example here would be, here we have a modulus 4 counter here, and we have a modulus 8 counter. Both of these counters are synchronous counters themselves. So let me see. In fact, I'm wrong actually. This is not asynchronous. This is asynchronous. This one is asynchronous. This one is also asynchronous, because here the clock signal is only feeding the first flip-flop. You can see. But if we can use these big blocks of modulus 4 counter and cascade it with another big block of the modulus 8 counter. And what comes to happen then is that the resulting modulus of the counters, combination of the two, would be the modulus of the first counter multiplied by the modulus of the second counter, not the addition. So this whole block together will be a modulus 32 counter. And the reason why this happens is because, remember, in this case Q1, which is this particular block, so if you look at it in a series of blocks, you will see that the clock signal activates Q1, activates Q0. So it divides basically Q0 by 2, the frequency of the clock by 2 here. So this one, Q0 will simply be half the frequency of the clock signal. and Q1 by extension will also be have the frequency of Q0. And if you use Q1 now as the input clock to Q2, then in that case, then you keep having these frequencies, having them, so that ultimately you have the modulus being the resulting modulus of the counter being the multiplication of the modulus of all of these counters. Because effectively, if you look at each one of these, this one, 2, 3, 4, 5, each one of them is like a modulus 2 counter. So you have two, so you have a modulus 2 counter multiplied by a modulus 2 counter multiplied by a modulus 2 counter, another modulus 2 counter, 5 of them, 5 times. So you have this 5 times, so which is like 2 to the power 5, which gives you 32, which is why there is a modulus 32 counter here. So you can also, as I explained, you can also cascade synchronous counters instead of asynchronous counters. And this is an example of a modulus 10 counter. And this is, if you look at one of these counters here, you'll see that this is a count enable, which has to be kept high for this to count. And then you have, in this case, a input clock frequency. And you have TC, which is terminal count, which gets only activated once when the terminal count is achieved. So when you reach your terminal count of 10, then TC will transition to go high. When you reach your count of 10, 10 being 10, 10. So when you're Q2 to Q0 becomes 10. At that transition, then the TC goes high, right? For that particular period only, and then it will go back again. So the way this will work, first of all, is that because you're cascading two of these counters, then the resulting modulus will be 10 by 10, which is a modulus 100 counter. Now the way it would work is the clock, the input clock here, would activate this counter to operate. So in the first instance, as you start, let's say the counters are all resetted to 0, 0, 0, 0, 0, 0, 0, 0. When that is the case, then the terminal count here will also be 0. So what then happens is, because the terminal count is 0, this will be 0 here. This counter is going to be disabled, which means it won't be activated by this clock signal that comes in here. This thing would be useless. So what would happen is, because this one is on high, the first counter number 1 will count. So it will count all the way from 0 to 10. Once it reaches 10, what then happens is that once it reaches 10, as we have explained initially, so once it reaches 10, then when it reaches that particular value of 10, at that particular transition, then this becomes 1. So it will enable this count. And once that count is enabled, in the next clock cycle, because this is enabled, then this counter will start counting 1. It will start counting 1. And then in the next cycle here, obviously in the next cycle, what will happen that it will go back to 0, 0, because it's a modulus 10 count. It will go back to 0, 0. And this will have only counted once. And then this cycle will repeat itself. This will count 10 more times up until that. And once it reaches another 10, this will have counted 2 now. And so on and so forth. So this counter number 2 will count once every 10 steps of counter number 1. So in that case, this one counts 10 times, this one counts only once. So every time this counts 10 times, that one counts only once. And because of that, this becomes then a modulus 100 counter. And the output frequency here is going to be divided by 100, and the output frequency here of the terminal account is going to be divided by 10. So in fact, we can put any variations of counters and cascade them. So in this case, if you have here a mod 8 counter, a mod 12 counter, a mod 16 counter, we can see that this creates a mod 8 times 12 times 16 counter. So we can multiply that. This will be the modulus of this new counter. And the frequency here of the output will be the primary frequency of the input, because the counter is like a frequency divider, divided by 8 times 12 times 16. The same thing will apply here. So this would be 10 mod 10 times 4 times 7 times 5 counter. And the frequency here of the input is going to be divided by 10 times 4 times 7 times 5. So in many applications, it's sometimes necessary to decode some states of a counter. So decoding a counter can be done using a decoder, or it can be done using a logic circuit. And a good example of a decoder or decoding of a counter is the terminal count function, which is given in this counter example. And this terminal count simply shows when the counter has reached its biggest value that it must count, which is 10. So it will go high as soon as the counter reaches terminal count. It will reset the count to a particular stage. In this case, it will just reset back to 0, 0. So the counter in this case will count from 0 all the way to the terminal count and then back. So at this stage, the terminal count will go up when the terminal count is reached, and then go down to the rest of the count. So the way the terminal count is implemented is using a decoding circuit. So this is an example of a 3-bit counter. So this 3-bit counter has 2 decoding circuits, and in this case we call them active high decoding, because we have AND gates. If NAND gates were used instead, we would have what's called active low decoding. So as you can see here, for instance, this output here detects a certain output. It detects a certain combination or a certain count in a counter. You will see that this is attached to Q2, and it's also attached to Q1, and it's also attached to Q0. So in fact, the output here, it's equivalent to Q2 and Q1 and Q0. And this is equivalent to detecting when the output is 111, that is, the output count is equal to 7, a decimal value of 7. And then this AND gate, on the other hand, detects the count of 2 because it's attached to Q2 bar, and it's attached also in the middle to Q1, and then the less significant bit here, it's attached to, trace it, it's attached to Q0 bar. So the count is Q2 bar, Q1, and Q0 bar, and this is equivalent to 010 base 2, which is equal to basically 2. Now, if we zoom in and look at the operation of the counter, we will see that the counter has the following behavior. So the counter will count as normal. For instance, it will move from 0, and then it will move to 1, and then it will move to 2, which is 0, 1, 0, and then it will move to 1, 1, 0, which is 3, and 0, 0, 1, which is 4, and 1, 0, 1, which is 5, 0 1 1, which is 6, and then here it will have 1 1 1, which is 7. So what tends to happen in this case is that, remember, Q7, sorry, the output 7 here is the AND gate of Q2, Q1, and Q0, which means the output 7 here is high when all of these three are high at the same time, which is why then the output of Q7 will only be high at this instance. On the other hand, 2, this output, it's high when you have Q2 bar, Q1, and Q0 bar. And this is high when you have 0, 1, 0. And this is the output here. Now, so in that case, these are active high decoder outputs, which can be able to detect these different codes. One other important issue to take note of is that in the real world, in reality, remember, because of propagation delays, there are always decoding glitches. There will always be decoding glitches, and decoding glitches will be caused by the fact that, if, say, for example, you look at the decoder outputs here, which are active low. So typically, what would happen here is, if you look at a case where a counter feeds a decoder, and in this case, if, say, the output here is 0 1 0 1, this is equivalent to a binary number. This is equivalent to binary number 10, right? If, on the other hand, we have an output like 1 0 1 0, because of this, the most significant bit is 0. This is 101, so it's like this one. This is equivalent to the binary number 5. And when that happens, the output here at 5 will be the one which is active, which means here we will have 0. And the rest of these are just going to be 1 1 1 1 1 1 1 1. So that's what's going to happen. However, because the counter changes with time, if you look at it as a waveform, you will see that it takes time for this input to propagate all the way to the output, because there's a propagation delay here, which is finite. And so because of that, the inputs of the decoder will glitch. So let's look at a case whereby you have a counter moving from 0 to 1, and then it wants to change to 2. Because remember, the Q outputs here would not necessarily change immediately with the input clock. In fact, if it's an asynchronous counter, you will see that Q3 will be the last to change. Even if it's a synchronous counter, you'll see that there is a propagation delay between the clock and the output changing. Because of that, in this transition, say for example, you're going to the next count, because as you're going to 2, the output here changes. At this stage, in fact, let me just start by saying, at this stage here, the output of the counter is 1, which means the only active output here will be 1, which is this one. The rest here will be inactive. So 1 will be 0, which is active. The rest will be inactive, which is 1 1 1 1, because the decoder output is active when it's low. It's an active low decoder. Now, when this changes to this 0 changes to a 1 in the next phase, because there is a time that it takes, a finite amount of time, there will be a time where whereby the output here, it's more, has not reflected on the input has not reflected. So you will have a count which is intermediate here, and this count will be 0 0 0 0, and because of that, the as this changes, this will deactivate the 1 and reactivate the 0 before it comes back and settles to the right value, which is the 2. Because at this stage it has to settle to 1, 0, 0, 0, which is a 2. So what will happen is that there will be a glitch at the output of the decoder. So the decoder will first activate the 0 and then activate the 2 instead of just straight away activating the 2. And if you follow the same logic, this would happen even as you transition from 2 to 3, because then there will be this transition which activates that, and then this will be activated, and then finally the final count of a 3 will then be activated. So these glitches will happen, and sometimes the circuits, the user applications making counters may malfunction. In order to prevent such occurrences, one of the techniques that's used is called strobing. Strobing simply means that the decoder circuit is disabled up until the outputs of the counter have settled. The values of the outputs of the counter have settled. So in this case, the clock, as it runs, it will only enable the decoder once the outputs of the counter are settled. So the decoder will only respond at the after the falling edge. So it will only respond whilst the clock, the value of the clock is at 0. Like here and here and here. So in this case, this will avoid the glitches, because then the decoder will only be activated once the outputs have settled. So let's look at now a typical example of where you would apply these counters. And one of the obvious examples is in the digital clock, the alarm of the digital clock. And in this digital clock, we see, for instance, that we will receive normally a sinusoidal waveform from a clocking device or timing device, which will be a sinusoidal, not necessarily a square wave, and there will be a wave shaping circuit to make it into a square wave so that the counters can start working. So in this case here, say for example, this would be a divide by 60 counter, because you've cascaded 10, a mod 10 counter and a mod 6 counter. So the modulus of this counter would be 6 times 10, which is 60, So, and this would simply be used to ensure that the clock ticks once each and every second, so for 1 Hz. So then that clock would then be used to keep track of time of the seconds, the minutes, as well as the hours. So if you look at this setup, the counter outputs are linked. They are linked to the 7-segment decoder here. So the BCD to 7-segment decoder. So they take in the BCD code and display it as a digit on the 7-segment decoder. And the counters here are linked using a terminal count output. So that the next counter is triggered once when the counter before it reaches its terminal count. So in this case here, this will count the 60 seconds, that will count the 60 minutes, and this will count the hour. Yeah, one of the first components of this counter is the divide by 60 counter. You can see that the first counter is a counter with a modulus of 10, so it will count from 0 to 9. And now the second one, it's a mod 6 counter. So mod 6 counter, the way it's made is that it's made in such a way that whenever it reaches a value of 6, it clears. So whenever it reaches this value of 6, and then it resets to 0, 0, so that the count can go. So this one can count only 6 times, and then this one counts 10 times, and then this will make a mod 60 counter. So what happens here is, once this counter reaches 60, this value should be 1, 1 1 0, and this, because of that, this will be, the output here will go low, and then if this goes low, the counter will start to clear, and then it will reset the next count to 0 0. And in this case, this will ensure that this counter only counts 60 seconds or 60 minutes. The other interesting bit here is the hour counter. So the hour counter in itself is meant so that it counts from 0 to 12 and back. So it will count 0 to 12 and then backwards. In this case, this is a 12-hour clock, it's not a 24-hour clock. So what will happen is that the JK flip-flop here will work as a mod 1 counter, sorry, mod 2 counter, and its count will either be 0 or 1. And the way it will work is that when the count output here reaches 9 is 0 0 0 1, that is when we have 1 0 0 1, the output here will be activated, and that will be activated, and this then will give you a 1 here. So you will get a 1 at the inputs to ensure that it then comes. So whenever you record the 9, it will make sure that in the next clock pulse it activates this 1, so that the JK flip-flop is set so that you can have a 1 in the next count. And then the decode circuit here will ensure that whenever the count reaches 12, the counter restarts in the next step. It restarts at 1. So what it will do is that when the count reaches 12, that is when you have a 1 in this side, and then a 12 this side, you'll have a 2 which is written like this. 0 0 1 0. So it will detect this 1, detect that 1, and then it will reset to make sure that the count hits 1 in the next step. So in this case, the counter in fact counts from 1 to 12, yeah. And another example is of an application of a counter would be an automobile parking control system. And this could be made for a parking lot where you want to count the number of vehicles in the parking lot, so that it can alert the person who wants to enter parking lot late that the parking is full, if the parking might be full. So for such an example, we will have, in this case, as an example here, we have a counter that counts 100 vehicles. The capacity of the parking lot is 100 vehicles. It uses a up-down counter. So you might have an instance where as a vehicle enters, it adds 1, and then as it leaves, it subtracts 1. So the display of such a system will ensure that the number that's been displayed here, it's accurate, and the person who is entering the parking lot can see if the parking lot is full or not. So the entrance will consist of these optoelectronic sensors to detect whether the vehicle is entering to create an up count, or if the vehicle is exiting to create a down count. So this will be an exit, and then this one is enter. So then what then happens is that this counter will then be used to be connected to an interface, and the interface can then detect if there's a full, if it's full, to indicate that the parking is full, and also to open and close the gate. In this example, so the parking lot system will have a modulus up-down counter, a modulus 100 up-down counter, which can be made up of a cascade of modulus 10 and a modulus 10 counter. So what happens is when the vehicle enters, this will activate the sensor at the S input, and then the latch will be at the set mode, so it will be 1 and 0, and then that will set the counter here to an up mode, up count. So it will send to an up count, and then the signal here at the input of the NOR gate will also activate this. Will then trigger the clock for the counters to count up. And in a similar fashion, when the vehicle exits, what will happen? This will trigger the reset mode, and then you'll have your 1 here and a 0 there at the input, and then your output here Q will go to the 1, which will then trigger a downward counting mode, and then this will reduce the count. And of course, this output will be for terminal count of the final counter to indicate if the parking lot is full or not. Another simple example is a parallel to serial data conversion. So this is typically a circuit which can be used in long range transmission, whereby the number of wires or cables that carry the signal is 1, but so that the information is carried on a serial on a single wiring to reduce the cost of wiring. So what will happen is that the digits or the information data D1, D2, D3, and so on and so forth would enter in parallel, but the clock will run at a certain speed here, so that it changes. As it changes, it selects different lines here, so that these different lines are connected in turn to the serial output. In that way, the serial data is in each turn of each clock cycle. During each clock cycle, the serial data is being transmitted from the parallel data in to the serial out data output. So this can be observed here by simply looking at the waveform. So this is the waveform of the select lines, which is the counter. So the counter will count normally as we expect to make 0, 1, 2, 3, 4, and so on and so forth. So what then happens is that as it does that, it connects different data lines. If it's 0, it will connect line 0. If it's 1, it will then connect line 1. If it's 2, it connects line 2, and so on and so forth. If you finish this part 4, you will go back then to revise the questions in the book, some of the questions in the book related to synchronous up-down counters. You will look at the cascading of counters and the issues involved. You will look at the decoding of counters and how it's done. And you will look at the applications of counters, the 2 applications which I have discussed, and one more which is given in the book.